In early October 2024, astronomers watching a visitor from beyond our solar system noticed something they had never seen before. The comet called 3I Atlas, which came from somewhere in the vast space between the stars, started changing colours in ways that broke every rule scientists thought they knew about comets. One week the cloud of gas around it glowed greenish. The next week it looked more orange. Then it shifted back again. This was not just a trick of the light or a problem with the telescopes. The chemistry itself was doing something completely unexpected, and even today the brightest minds studying space cannot fully explain what they are seeing. Why would a frozen ball of ice and rock from another star system behave so strangely? What could make its colours dance and shift like this? And what does this tell us about the mysterious space between stars, the place this traveller has been wandering for millions or maybe billions of years? Stay with me, and we will walk through one of the most puzzling mysteries in astronomy right now, a mystery that is challenging everything. We thought we understood about comets and the materials that drift through the darkness of space. Let's begin at the beginning. 3I Atlas arrived in our solar neighbourhood in late 2023. Astronomers spotted it because it was moving in a very unusual way. Most comets that visit us come from two places. Some come from the Kuiper Belt, a region of icy objects beyond Neptune. Others come from the Oort cloud, an enormous sphere of frozen chunks surrounding our solar system far beyond Pluto. These are local comets, born in our own cosmic backyard when the sun was young. But 3I Atlas came from somewhere else entirely. Its path through space showed scientists that it did not orbit our sun. It was just passing through, a wanderer from the space between stars. This makes 3I Atlas only the third known interstellar object ever detected visiting our solar system. The first was Oumuamua, discovered in 2017, a strange rocky object shaped like a cigar or perhaps a pancake, depending on who you asked. The second was 2E Borisov, spotted in 2019, which looked more like a normal comet with a tail. Now we have 3I Atlas, and it is proving to be the weirdest of them all. When a comet gets close to the sun, it starts to warm up. Remember, comets are mostly made of ice, frozen gases, dust, and rock all stuck together. As the sun's heat reaches them, the ices begin to turn into gas, a process called sublimation. It is like when a puddle of water evaporates on a hot day, except this happens with frozen materials much colder than regular ice. The gases puff out from the comet's surface, creating a huge cloud around the solid centre. This cloud is called a coma. The coma can be thousands or even millions of kilometres wide, much bigger than Earth. Sometimes the gases and dust get pushed away from the sun by solar wind and sunlight pressure, creating the beautiful tail we see in pictures of comets. Scientists love studying comets because they are like time capsules. They contain materials from when our solar system formed, over 4.5 billion years ago. Most of that material has been cooked and changed by being near the sun, or smashed together to make planets. But comets stayed frozen in the outer darkness, preserving the original ingredients. When we study what comets are made of, we learn about the early solar system, and when we study an interstellar comet like 3I Atlas, we might learn about a completely different star system, maybe 100s of light years away. Here is where things get fascinating. When 3I Atlas started getting closer to the sun in late 2023 and early 2024, telescopes around the world turned to watch it. Astronomers use special instruments that can split light into its different colours, a technique called spectroscopy. Different chemicals give off different colours of light when they are heated or energised. It is like a fingerprint. Carbon monoxide makes one pattern of colours, water makes another, cyanide compounds make another. By looking at the spectrum of light coming from the coma, scientists can figure out exactly what gases are puffing out of the comet. The first surprise came when researchers found unusual amounts of carbon dioxide coming from 3I Atlas. Now, carbon dioxide is not unusual in comets. It is frozen on many of them, but the amounts and patterns they saw were odd. Then came the second surprise, and this one was truly bizarre. Astronomers detected atomic nickel vapour in the coma. Let me say that again in a different way so it is clear. There was nickel metal in gas form floating in the cloud around this comet. This had never been seen before in any interstellar object and is extremely rare even in comets from our own solar system. Nickel is a metal. It does not just float around in space as a gas under normal conditions. It needs to be very, very hot to turn into vapour, much hotter than what you find in the outer parts of a comet's coma where the gas cloud is. Scientists measured the temperature where they found the nickel vapor, and it was far too cold for nickel to naturally be in gas form. It should have been solid, like the nickel in a coin in your pocket. But there it was, clearly detected, floating in space. One group of researchers using the Very Large Telescope in Chile confirmed this finding. They published their work and other scientists checked it. The nickel vapor was real. Now imagine you are a scientist who has studied comets your whole career. You think you understand the basic rules. Comets are cold, they are made of ices and dust and rock. When they warm up, the ices evaporate. The dust drifts away. The process is fairly predictable. Then you see a comet releasing metal vapor at temperatures where that metal should not be a vapor at all. This is like watching ice cubes melt in a freezer. It breaks the rules, and when nature breaks the rules we think we know. It usually means we are missing something important. The color changes made the mystery even deeper. The coma of 3-di Atlas shifted between greenish tones and orange or reddish tones over a period of weeks. Scientists tracked these changes carefully. Green colors in comets usually come from a molecule called dicarbon. This forms when carbon monoxide breaks apart in sunlight, and the carbon atoms stick together in pairs. Dicarbon glows green. Many comets have a greenish tint because of this. Orange and red tones often come from different chemicals, including certain kinds of dust particles and molecules with sodium or other elements. What puzzled everyone was how quickly the colors changed and how they did not match the expected patterns. If the comet was just releasing one steady stream of gases as it got warmer, the color should have been fairly constant or changed slowly and predictably as it got closer to the sun. But 3-i Atlas was not following that script. Its chemistry seemed to be turning on and off like a switch, or cycling through different modes that no one could predict. One team of researchers said it was like the comet had different chemical recipes in different parts of its surface, and as it spun, different recipes got their turn facing the sun. Let's think about what might cause this. Picture the surface of 3-i Atlas as a patchwork. Maybe some areas are rich in carbon dioxide ice, other areas have more water ice, still other patches might have concentrations of organic molecules, which are carbon-based chemicals more complex than simple gases like carbon monoxide. As the comet rotates, different patches face the sun at different times of day. When a carbon dioxide-rich patch is lit up, one set of gases puffs out and the coma glows one color. When a different patch rotates into sunlight, a different mix of gases is released, and the color shifts. This would be like a slowly spinning disco ball where each mirror is a different tint. The overall color of the light bouncing off changes as it turns. That sounds reasonable, and it might explain some of what we see. But it does not explain the nickel vapor, and it does not explain some of the other very strange measurements scientists made. For example, the ratios of different carbon-based molecules in the coma kept changing. Ratios are comparisons. If you have 10 carbon monoxide molecules for every 1 carbon dioxide molecule at one moment, then an hour later you have 5 carbon monoxide molecules for every 1 carbon dioxide molecule. That ratio has changed. In normal comets, these ratios might change a little as the comet gets closer to the sun and heats up more, but they change gradually and predictably. 3-i Atlas was jumping around. Some researchers started to wonder if the comet's surface was not just a simple mixture of ices, but something more complex. Maybe there were layers. Imagine a layer cake. The top layer might be one flavor, and just beneath it is a different flavor. If the top layer wears away or cracks, suddenly you are tasting the second layer. On a comet, the sun's heat and the force of gases escaping could blow away or crack the top layer of ice, exposing a layer underneath with a different chemical recipe. If this happens in bursts or in certain spots, you could get sudden changes in what gases are released and what colors appear. Another idea involves something called clathrates. A clathrate is a structure where one kind of molecule, usually water ice, forms a cage that traps other molecules inside. Think of it like a tiny ice prison holding a gas molecule. Clathrates are stable at very cold temperatures, but when they warm up past a certain point, the cage breaks apart and the trapped gas suddenly bursts out. If 3-i Atlas has clathrates in its ice, then as different parts warm up, you could get sudden releases of trapped gases. This might explain some of the unexpected bursts of activity and chemical changes. Scientists know that clathrates exist in some solar system comets, and possibly on moons like Saturn's Titan. But the behavior of 3-i Atlas seemed more extreme than what clathrates alone would predict. Then there is the nickel mystery. Where is the nickel coming from, and why is it in vapor form? One possibility is that the comet contains tiny grains of metal mixed into the ice and dust. These grains could be extremely small, much tinier than a grain of sand. When the ice around them evaporates and they are exposed to direct sunlight in space, maybe the sunlight heats them up so much that the metal actually starts to evaporate off the grain. But the math on this is tricky. The grains would have to be very tiny and very spread out in the coma to reach high enough temperatures, and even then, it is hard to make the numbers work to explain the amount of nickel vapor detected. Another idea is that the nickel is not coming from metal grains at all, but from organometallic compounds. An organometallic compound is a molecule where a metal atom is bonded to carbon atoms or other organic parts. These compounds can be fragile. When sunlight hits them, they break apart, releasing the metal atom. If 3I Atlas contains organometallic molecules with nickel, then sunlight could break them down and free the nickel atoms into the coma as vapor. This is an exotic idea because organometallic compounds are not common in space, at least not that we have detected very often. But an interstellar comet might contain materials made in a very different environment than what we are used to. Maybe the star system where 3I Atlas formed had different chemistry. Maybe it formed in a region of space rich in certain metals and organic molecules that bonded together in unusual ways. Scientists are also considering whether the strange chemistry could be linked to the comet's long journey through interstellar space. 3I Atlas likely spent millions or billions of years out there in the cold darkness between stars. In that environment, the comet would have been bombarded by cosmic rays. Cosmic rays are high-energy particles, mostly protons, zipping through space at nearly the speed of light. When they slam into ice and rock, they can cause chemical reactions. They can break molecules apart and allow atoms to recombine in new ways. Over millions of years, cosmic ray bombardment could alter the surface chemistry of an interstellar comet in ways we do not fully understand. Maybe this processing created unusual compounds that now, warmed by our sun, are breaking down and releasing unexpected gases and vapors. Let's step back for a moment and think about the bigger picture. We only know of 3 interstellar objects so far. Oumuamua came through and left quickly. Scientists got a brief look, and it was puzzling. It did not have a visible coma or tail like a comet, but its trajectory changed slightly, as if something was pushing it. Some researchers think it was outgassing, releasing gas we could not see, which acted like a tiny rocket. Others proposed more unusual ideas. We still do not have a definitive answer about what Oumuamua was made of. Tui Borisov, the second visitor, looked more like a normal comet. It had a coma and a tail. Its chemistry seemed familiar, mostly water and carbon monoxide, similar to comets from our solar system. That made scientists feel a bit relieved. Maybe interstellar space was not so different after all. Maybe the building blocks of planetary systems were similar everywhere, but now 3I Atlas has arrived, and it is telling a different story. It is showing us that interstellar comets can be weird, that they can contain chemistry we do not expect, and that they can behave in ways that challenge our models. This is actually exciting for science, even though it is also frustrating. When we find something we cannot easily explain, it means there is more to learn. It means our understanding is incomplete, and that is an invitation to dig deeper, to come up with new ideas, and to make new discoveries. Let me tell you about some of the teams working on this mystery right now. In late 2024, a group of astronomers from the European Southern Observatory, working with colleagues in the United States and Japan, published detailed observations of 3I Atlas taken over several months. They used multiple telescopes to track how the brightness and color of the coma changed with time and with the comet's distance from the sun. Their paper presented graphs and data showing the fluctuations. They proposed the patchy surface model I mentioned, suggesting that different areas of the comet's surface have different compositions. They also noted the nickel vapor and admitted they did not have a complete explanation. Their conclusion was cautious. They called for more observations and more laboratory experiments to test different ideas. Around the same time, a team at a university in the Netherlands used computer models to simulate what might happen if a comet like 3I Atlas contained clathrate structures. They ran the simulations with different assumptions about how much gas was trapped, how the clathrates were distributed, and how fast the comet was rotating. Their results showed that clathrates could cause some bursts of gas release, but the model did not fully match the real observations. The color changes in their simulation were not as dramatic as what was actually seen. They suggested that maybe clathrates were part of the story, but something else was happening too. Another research group, this one based in California, focused on the nickel mystery. They did lab experiments where they took tiny grains of nickel-iron metal, like what might be found in meteorites, and blasted them with intense light to simulate the sun. They measured how much the grains heated up and whether they started releasing metal vapor. Their results were interesting. Under some conditions, the smallest grains did release a tiny bit of vapor, but far less than what 3I Atlas was producing. The researchers concluded that simple thermal evaporation of metal grains probably was not the main answer. They suggested looking for organometallic compounds or some other exotic source. Meanwhile, scientists who study the chemistry of interstellar space itself, not just comets, started weighing in. They pointed out that the space between stars contains very thin gas and dust, along with complex organic molecules. Radio telescopes have detected over 200 different molecules floating in interstellar clouds, including alcohols, sugars, and even amino acids, which are the building blocks of proteins. If 3I Atlas formed in or passed through regions rich in these complex molecules, it might have picked up or incorporated materials we do not usually see in solar system comets. Some of those materials might include metal atoms bonded into organic structures. In early 2025, a new piece of the puzzle emerged. A team using data from the James Webb Space Telescope, which can see in infrared light, detected faint signatures of more complex organic molecules in the coma of 3I Atlas. Infrared light is light with wavelengths longer than what our eyes can see. It is good for detecting warm objects and certain kinds of molecules. The Webb data showed hints of hydrocarbons, which are molecules made of hydrogen and carbon, and possibly even some nitrogen-bearing compounds. The data was preliminary and hard to interpret, but it suggested the comet's chemistry was even richer and more complex than the earlier visible light observations had shown. The researchers who analysed the Webb data said more observations were needed to confirm and identify the specific molecules, but if confirmed, it would add another layer to the mystery. Why does this interstellar comet have such a complex and varied chemistry? One way to think about all this is to compare it to tasting a dish you have never eaten before. You take a bite and you taste something sweet. Then you take another bite and you taste something spicy. A third bite is sour. You realize the dish has many ingredients, and they are not evenly mixed. Each bite samples a different combination. 3. Atlas is like that dish. Each moment, as it rotates and as different parts of it are warmed by the sun, we are sampling a different combination of its ingredients. And because it came from another star system, the ingredients themselves might be exotic, things we do not have much experience with. Now let's talk about what this means for understanding the bigger universe. If interstellar comets are common, and if many of them carry complex organic chemistry and unusual materials, that has important implications. Organic molecules are the foundation of life. Life as we know it requires carbon-based molecules, water, and energy. If interstellar space is full of comets carrying organic molecules, then those molecules are being spread around the galaxy. When a star system forms, some of these interstellar comets might get captured. They would deliver their organic cargo to the new planets forming around the young star. This could help seed planets with the chemical ingredients needed for life to start. Earth's water and organic molecules might have partly come from comets and asteroids that smashed into our planet billions of years ago, back when the solar system was young and chaotic. If interstellar comets also contributed, even a little bit, then the building blocks of life on Earth might have come from beyond our solar system. That is a profound thought. It means we might be made in a tiny way from materials born around another star, perhaps a star that died long before our sun was born. Scientists also wonder whether studying interstellar comets can tell us about planets we cannot see. Planets around other stars, called exoplanets, are hard to study in detail. Even the biggest telescopes can only detect their presence and measure some basic facts like size and orbit. We cannot easily sample their atmospheres or surfaces. But if a comet from another star system visits us, it is like getting a free sample delivered to our doorstep. By analysing 3I Atlas, we might learn something about the chemistry of the star system it came from. Was it a system with a lot of metals? Was it rich in carbon? Did it have plenty of water? These clues can help us understand the diversity of planetary systems in the galaxy. Of course, there is a big unknown here. We do not actually know which star system 3I Atlas came from. Its trajectory shows it came from the general direction of the constellation Ursa Major, the Big Dipper. But space is vast. and the comet has been travelling for so long that tracing it back to a specific star is almost impossible. It could have been wandering for 10 million years or 100 million years. During that time, stars move. The star it came from might now be in a completely different part of the sky. So we can study what 3I Atlas is made of, but we may never know where it was born. It is like meeting a stranger and learning about their personality and habits, but never finding out what city they grew up in. Still, every bit of data is valuable, and scientists are not giving up on the mystery of the colour changes and the strange chemistry. New observations are being planned. Some teams want to use space-based telescopes to watch the comet for longer periods without weather or daylight interrupting. Others want to get spectra with even higher precision, breaking the light into finer details to spot molecules that might have been missed. There is talk of using radar to bounce radio waves off the solid nucleus of the comet to learn its size and shape more exactly. Every new piece of information might help fit the puzzle together. One fascinating aspect of this whole story is how much we still do not understand about comets in general, even the ones from our own solar system. Comets have surprised scientists again and again. In the 1990s, the comet Hale-Bopp became very bright and was visible to the naked eye for over a year. Studies of its chemistry revealed a richness no one expected, including molecules like methane and ethane. In 2014, the European Space Agency's Rosetta spacecraft orbited the comet 67P Churyumov-Gerasimenko for 2 years, and even landed a small probe on its surface. Rosetta's data was full of surprises. The comet's water had a different isotopic ratio than Earth's water, suggesting maybe Earth's water did not all come from comets like that one. The comet's surface was harder and more varied than expected, with smooth plains next to rough cliffs. Organic molecules detected included glycine, an amino acid. Every mission, every detailed study of a comet teaches us that these objects are more complex than we thought. 3I Atlas is adding to that humility. It is reminding scientists that the universe is full of variety. Just because we understand some comets fairly well does not mean we understand them all, especially the ones coming from completely different environments. And that is okay. Science is a process. It does not have all the answers right away. Scientists make observations, form hypotheses, test them, and slowly build up a better picture. Sometimes the picture changes completely. That is not failure. That is progress. Let's talk for a moment about what happens next for 3I Atlas itself. Comets that pass close to the Sun can change dramatically. The Sun's heat can cause big pieces of ice to break off, or cause the whole comet to split apart. Some comets have broken into several pieces right in front of astronomers' eyes. Others have gotten so close to the Sun that they evaporated completely, plunging into the Sun's atmosphere and disappearing. 3I Atlas fortunately did not get that close. Its closest approach to the Sun, called perihelion, was at a safe distance, roughly around the orbit of Mars or a bit closer. At that distance, it got warm enough to produce a coma and release gases, but not so close that it was in danger of breaking up. After passing the Sun, 3I Atlas is now heading back out of the solar system on the other side. Its speed is so high and its trajectory is so steep that the Sun's gravity cannot hold it. It will leave our solar system just as it came, a wanderer moving on to the next phase of its endless journey through the galaxy. This means our time to study it is limited. Already, by late 2025, 3I Atlas is getting farther from the Sun and cooling down. The coma is getting fainter as less gas is released. The colour changes are becoming harder to see. Within a few years, it will be too far and too dim for most telescopes to observe. It will fade back into the darkness of deep space, just one more tiny speck among countless stars. Scientists are rushing to gather as much data as they can before it is gone. Every observation now is precious, because once 3I Atlas is too far away, we may never see it again. And who knows when the next interstellar comet will arrive? It could be next year or 100 years from now. We have no way to predict. This sense of urgency is part of what makes astronomy exciting. The universe puts on shows, but they are usually brief. A supernova flares up and fades over weeks. An asteroid passes close to Earth for one night. A comet swings by the Sun once and then leaves. Astronomers have to be ready, have to be watching, and have to move quickly, and they have to share their data and work together, because no single telescope or single team can do it all. The discoveries about 3I Atlas came from many groups around the world, using different telescopes and different techniques, all sharing their results and building on each other's work. That cooperation is one of the beautiful things about science. Before we move on, I want to leave you with a thought. 3. I Atlas is changing colour because of chemistry we cannot yet explain. It is releasing nickel vapour at temperatures that should not allow it. It is showing us that even something as seemingly simple as a frozen ball of ice and rock can be full of mysteries. And here is the thing about mysteries. They are not frustrating dead ends. They are invitations. They are the universe saying, there is more here, keep looking, keep thinking, keep trying. Every answered question leads to new questions. That is how knowledge grows. 3. iAtlas is giving us new questions, and scientists are eager to chase the answers, even if it takes years or decades. Now, let's broaden our view. 3 iAtlas is not the only object capturing attention in the space community right now. There are other visitors, other mysteries, other pieces of the cosmic puzzle being discussed and studied. Let's talk about some of them. Oumuamua, the first interstellar visitor, that still puzzles us before 3. iAtlas, before 2 I Borisov. There was Oumuamua. Discovered in October of 2017 by the Pan-STARRS telescope in Hawaii, Oumuamua was the first object ever confirmed to have come from outside our solar system. Its name means scout, or messenger, in Hawaiian, a fitting title for humanity's first known contact with an interstellar traveller. But even though several years have passed since its discovery, Oumuamua remains deeply mysterious, and scientists are still arguing about what it actually was. When astronomers first spotted Oumuamua, it was already on its way out of the solar system. It had passed its closest point to the Sun and was heading back into deep space. This meant scientists had only a short window of time to study it before it became too faint to see. Telescopes around the world swung into action, gathering every bit of data they could. What they found was strange. Oumuamua was moving faster than it should. Its trajectory showed it was accelerating slightly as it moved away from the Sun, as if something was pushing it. This was unexpected because asteroids and regular solar system objects do not speed up like that unless something gives them a push. The most common explanation for acceleration in a comet is outgassing. When ice on a comet evaporates, the gas jets out into space, and by Newton's third law, for every action there is an equal and opposite reaction, the comet gets pushed in the opposite direction. It is like a very slow and gentle rocket engine. Many comets show this kind of non-gravitational acceleration, and it is easy to spot because they also have bright comas and tails from all the gas and dust they are releasing. But here is the puzzle. Oumuamua did not have a visible coma or tail. Astronomers looked hard and could not find any sign of gas or dust coming off it. Yet it was accelerating. So if it was not outgassing in the normal way, what was pushing it? One idea is that it was releasing gas, but the gas was made of molecules that do not reflect sunlight well and do not glow, so we could not see them. For example, if Oumuamua was releasing pure hydrogen gas or nitrogen gas, those would be invisible or nearly invisible to most telescopes. The gas would still provide thrust, but we would not see a coma. Some scientists built models showing this could work if the object was made mostly of hydrogen ice or nitrogen ice. Both of those ices are much more fragile than water ice and would evaporate at cooler temperatures and farther from the Sun. Another possibility is that Oumuamua was not outgassing at all, and the acceleration came from something else. One team of researchers suggested it might be covered in a layer of organic material that, when warmed by the Sun, released trapped gases in bursts. Another idea is that radiation pressure from sunlight itself was pushing it. Sunlight carries momentum, and when it hits an object, it exerts a tiny force. Usually this force is way too small to matter for anything bigger than a dust grain. But if Oumuamua was very light for its size, thin and flat like a sheet of paper or a sail, then sunlight pressure could have a noticeable effect. This led to some speculation, including the controversial idea by Harvard astronomer Avi Loeb that Oumuamua could be an artificial object, a kind of solar sail from an alien civilization. Most scientists are skeptical of this idea, not because it is impossible, but because there is no direct evidence for it, and because natural explanations, while not perfect, are more likely given what we know. The shape of Oumuamua added to the mystery. From the way its brightness changed as it tumbled through space, astronomers calculated it must be highly elongated. Early estimates suggested it could be roughly 10 times longer than it was wide, shaped like a cigar or a needle. Other studies, using different assumptions, suggested it might be flat and round, like a pancake or a disc. Without a close-up picture, we cannot know for sure. But either way, such an extreme shape is unusual. Most asteroids and comets are more round or potato-shaped. Why would an interstellar object be so stretched out or so flat? One hypothesis is that Oumuamua is a fragment, a piece broken off from a larger body. Maybe long ago it was part of a planet or a moon that got shattered by a collision, or torn apart by gravitational forces near a star. The fragment could have been stretched or flattened in the violence of that event. Then it got kicked out of its home system and started the long drift through interstellar space. Another idea is that it formed in an unusual way, perhaps in a disk of material around a young star where conditions were different than in our solar system. There are so many possibilities and so little data to narrow them down. By mid-2018, Oumuamua had faded from view. It is now far beyond the reach of even our most powerful telescopes, a tiny dark speck moving through the black between stars. We will never get another look at it unless we send a spacecraft after it, and that would be an enormous challenge. Oumuamua is moving at about 26 kilometers per second relative to the Sun. To catch up to it, a spacecraft would need to be incredibly fast, and would have to have been launched soon after discovery. Some engineers have sketched out concepts for an Oumuamua intercept mission, but it would be expensive and technically difficult, and the object is already so far away that even moving at high speed it would take decades to reach it. Still, the idea is out there. Maybe someday, if we develop faster propulsion systems, we could send a probe to chase down an interstellar visitor and see it up close. In the meantime, Oumuamua remains a puzzle and a reminder. It reminds us that the galaxy is full of objects drifting between stars, and we're only just beginning to notice them. It challenges us to think carefully about what we assume and to be ready for surprises, and it has sparked a lot of discussion and research, which is a good thing. Even if we never fully understand Oumuamua, the questions it raised have made scientists look more carefully at other objects, develop better detection methods, and think harder about the diversity of things that exist in space. 2. I Borisov, the more familiar interstellar comet. In August of 2019, an amateur astronomer named Gennady Borisov, working at his personal observatory in Crimea, discovered a new comet. At first, it seemed like a normal comet. But as more observations came in, astronomers realized its orbit was hyperbolic, meaning it was not bound to the Sun. It was moving too fast to be captured by the Sun's gravity. This was the second interstellar object ever detected, and it was given the designation 2E Borisov, with the I standing for interstellar, and the number indicating it was the second one found. Unlike Oumuamua, 2A Borisov looked like a proper comet. It had a bright coma full of gas and dust. It developed a tail as it got closer to the Sun. For scientists who study comets, this was a relief and a gift. Here was an interstellar comet that behaved in a familiar way, something they could study with the tools and techniques they already knew. Telescopes around the world and in space observed 2E Borisov intensely during its pass through the inner solar system in late 2019 and early 2020. Spectroscopy showed that its coma contained water vapor and carbon monoxide, two of the most common gases in solar system comets. The ratio of carbon monoxide to water was a bit higher than average for solar system comets, but not wildly different. It looked like 2E Borisov was made of similar stuff as the comets born around our Sun. This was interesting because it suggested that comet formation might be a fairly universal process. No matter which star system you look at, if planets are forming and icy bodies are getting flung into the outer regions, they might end up looking similar. Astronomers also measured the dust coming off 2E Borisov. The size and properties of the dust grains matched what is seen in many solar system comets. The nucleus, the solid core of the comet, was estimated to be somewhere around 1 kilometer across, maybe a bit less, a fairly typical size. The comet was active, releasing plenty of gas and dust, which made it relatively easy to study. In fact, 2I Borisov became bright enough that even amateur astronomers with backyard telescopes could see it, a rare treat. One of the exciting observations came from the Hubble Space Telescope. Hubble took detailed images and spectra of 2E Borisov, including measurements that showed the coma had a strange reddish colour in some parts. The red colour might have come from organic molecules, complex carbon-based compounds, possibly similar to the tholins found on some moons and dwarf planets in our solar system. Tholins are reddish or brownish organic materials formed when simpler molecules are broken apart by ultraviolet light or cosmic rays, and then recombine into more complex forms. If 2I Borisov contained tholins, it would mean that complex organic chemistry happens in other star systems too, which has implications for the potential for life beyond Earth. Another interesting finding was that 2I Borisov seemed to be quite fragile. In early 2020, observations showed that the comet brightened suddenly, a sign that a piece of it might have broken off. Comets can be delicate. They are held together by ice, and when that ice evaporates unevenly, stresses can build up and cause chunks to crack off. The fact that 2I Borisov may have partially fragmented was not too surprising, but it did limit how long scientists could study it. By mid-2020, it was fading as it moved away from the Sun and back out into the depths of space. Like Oumuamua, it is gone now, too distant and too faint to see. Still, the data collected from 2I Borisov was rich and valuable. Scientists wrote dozens of research papers analysing its composition, structure, and behaviour. The general conclusion was that while 2I Borisov was an interstellar visitor, it was not radically different from solar system comets. It fit broadly within the range of what we already knew. This was comforting in a way. It suggested that our understanding of comets was on the right track. But it also made 3I Atlas, with its strange colour changes and unexplained chemistry, stand out even more. If 2I Borisov was the well-behaved visitor, 3I Atlas is the wild card. Now that we have detected 3 interstellar objects, astronomers are eager to find more. The question is, how common are these visitors? Are they rare, with only one passing through the inner solar system every few years? Or are they actually quite common, and we just have not been looking carefully enough? New telescopes and surveys are being designed specifically to catch more of these interstellar wanderers. One of the most important projects is the Vera C. Rubin Observatory, currently under construction in Chile. This observatory will have a huge camera, the largest digital camera ever built for astronomy, and will scan the entire visible sky every few nights. It is designed to catch anything that moves or changes, including asteroids, comets, supernovae, and yes, interstellar objects. When the Rubin Observatory starts full operations, expected in the mid-2020s, scientists predict it will detect interstellar visitors much more frequently, maybe several per year. This will give us a much better sense of how many of these objects are out there and what they are like. There are also space-based missions in the works. NASA's upcoming Sphere-X mission, set to launch in the next few years, will survey the sky in infrared light. While its main goal is to study galaxies and the large-scale structure of the universe, it may also spot interstellar objects that are too faint or too cool to be easily seen by ground-based telescopes. And the James Webb Space Telescope, already in operation, can be directed to observe interstellar objects in great detail if they're discovered in time. Scientists are also developing better alert systems. When a new fast-moving object is spotted by one telescope, the information needs to get to other astronomers quickly so they can follow up with more observations before the object gets too far away. Networks of amateur and professional astronomers are coordinating to share data and mobilize telescopes around the world. The idea is to create a global rapid response system for interstellar objects, ensuring that when the next one comes, we do not miss the chance to study it. Researchers are also thinking about sending missions to intercept interstellar objects. This is much harder than sending a mission to a comet or asteroid in our own solar system, because interstellar objects are moving so fast. But it is not impossible. One concept being studied is a mission that would stay in a kind of standby orbit, ready to launch on short notice when an interstellar object is detected. The spacecraft would need a powerful propulsion system, perhaps using ion engines or even solar sails, to accelerate quickly and match the object's trajectory. If we could get a spacecraft close to an interstellar visitor, we could take close-up pictures, sample the gases in its coma, maybe even land on it and collect a piece to bring back to Earth. This is the dream of many planetary scientists, and while it is technologically challenging, it is becoming more feasible as propulsion and detection technologies improve. Every interstellar object that visits our solar system is a messenger from a distant place and time. By studying them, we can learn about star systems far away, about the materials that exist in the space between stars, and about the history of the galaxy itself. Think about it this way. Stars form from giant clouds of gas and dust in space. When a star ignites, the leftover material around it forms a disk, and from that disk, planets, asteroids, and comets are born. But not everything stays in the system. Gravitational interactions between planets can fling smaller objects out into space at high speed. These objects become interstellar, wandering the galaxy. Over billions of years, the galaxy has become filled with a vast population of these wanderers, objects that were once part of planetary systems but are now drifting alone. Estimating how many interstellar objects there are is tricky, but some scientists have tried. Based on the rate at which we have detected them, and making assumptions about how good our detection methods are, researchers estimate there could be thousands or even millions of interstellar objects passing through the inner solar system at any given time. Most of them are too small and too faint for us to see. We only notice the bigger ones, or the ones that get close enough and bright enough to stand out. But they are there, an invisible river of cosmic debris flowing past us. This population of interstellar objects is like a fossil record of the galaxy. Each object carries information about where it came from. The composition of an interstellar comet, for instance, might tell us about the chemistry of the star system that ejected it. If we find an interstellar object rich in water and carbon, it suggests it came from a system where those elements were abundant, perhaps a system like ours. If we find one with unusual metals or rare molecules, it might hint at a more exotic origin, maybe a system that formed in a different part of the galaxy where the mix of elements was different. Over time, as we study more and more interstellar visitors, we can start to build a picture of the chemical diversity of the galaxy and how it has changed over time. There is also the fascinating question of whether life could hitch a ride on interstellar objects. This idea is called panspermia. The basic concept is that life, or at least the building blocks of life, could be spread from one star system to another by comets and asteroids. If a comet covered in organic molecules, or maybe even carrying frozen microbes, gets ejected from a planet where life exists and eventually lands on another planet in another star system, it could seed that planet with life, or the ingredients for life. This is a speculative idea, and there is no direct evidence for it yet, but it is not completely far-fetched. We know that some bacteria on Earth can survive extreme cold and radiation. We know that organic molecules are common in space, and we know that interstellar objects do travel between star systems. Whether life could actually survive such a journey, which could take millions of years, is an open question. But studying the chemistry and biology of interstellar objects is one way to explore this idea. 3I Atlas, with its complex organic chemistry and unusual behavior, adds a small piece to this big puzzle. It shows that interstellar objects can carry a diverse mix of molecules, including carbon-based compounds. If those compounds can survive the harsh conditions of space, and if they can be delivered to planets, then maybe the building blocks of life are spread more widely across the galaxy than we thought. Maybe life is not as rare as we fear. Maybe the universe is full of places where the right ingredients have come together, and we just have not found them yet. As we close this exploration, let's come back to where we started. 3. I-Atlas is changing colour in ways that break the rules. It is releasing nickel vapour at temperatures that should not allow it. It is challenging scientists to rethink their models and come up with new explanations. And that is exactly what science is supposed to do. Science is not about having all the answers. It is about asking the right questions, making careful observations, testing ideas, and being willing to say, I do not know, but I am going to keep looking. 3I Atlas is a reminder that the universe is vast and full of surprises. It is a reminder that even in our own solar system's backyard there are mysteries waiting to be solved. And it is a reminder that every new discovery, every strange observation, is an opportunity to learn something new about the cosmos and our place in it. The colour-changing comet from another star system is telling us a story, and we're only just beginning to understand the words. But that is okay. We have time, we have curiosity, and we have the tools and the will to keep listening, keep watching, and keep searching for answers. And one day, maybe soon, the chemistry we cannot explain today will become the chemistry we understand tomorrow, and then we will look up, see the next mystery, and start the process all over again. That is the beauty of science, and that is the gift that 3I Atlas has given us.